the Sustainability Management Master's Program, you are answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. But at the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact. It's a pleasure to introduce today's speaker, Josh Wilson. So today's seminar is sponsored by the joint sponsor of the seminar series, WSP. So Josh is a senior engineer at WSP USA with over 10 years of experience specifying, managing, and delivering acoustic projects in various sectors. So he's currently leading WSP's global underwater acoustics practice area. So Josh is an active member of the Institute of Acoustics in the United Kingdom and the Institute of Noise Control Engineering in the US. So Josh obtained his BSc in Acoustics and Music at the Institute of Sound and Vibration Research at the University of Southampton, UK. So today, Josh will talk about underwater noise impacts of large-scale renewable energy offshore infrastructures. So welcome, Josh.
Awesome. Yeah, thanks, Dibs. And hi, everyone. Thanks for having me here. So as Dibs said, I'm Josh Wilson, and I'm an environmental engineer at WSP USA and work out of our New York City office. As you can probably tell, I'm not originally from the US and was originally with WSP UK in London before I moved across the US team at the beginning of last year, spent some time down in our Dallas office and now in New York. I'm a subject matter expert in acoustics and have worked for the last 10 years in environmental acoustics, underwater acoustics type applications for several sectors, but mainly for energy type projects all across the world. So today, I'll be mainly talking about a cool renewable offshore infrastructure project I've been working on for the last few years. Specifically, I'll be talking about the approach to underwater noise impacts in the context of environmental impact assessments. So I'll first cover what an environmental impact assessment is and why it's important in terms of sustainability. Then I'll discuss this particular project, and then I'll move into the underwater noise aspects. So, an environmental impact assessment, or EIA, is a process used to evaluate the potential environmental effects of a proposed project before it is approved or carried out. It considers several different factors, such as air pollution, water pollution, biodiversity loss, socio-economic impacts, and more specifically for marine type projects, it will consider impacts on marine mammals, fish, marine archaeology, and many other types of disciplines. The goal is to ensure that decision makers have all relevant environmental information before granting permits or approvals. So environmental impact assessments are a critical tool for sustainability, ensuring that development projects minimize harm to the environment while promoting long-term economic and social benefits. By evaluating potential environmental consequences before projects begin, EIAs help balance development with ecological preservation, resource conservation, and climate resilience. So EIAs have several different components, which I've split out here. So first of all, there's typically some sort of screening exercise, which determines whether a project requires an EIA. Then there's a scoping exercise where we identify the key environmental concerns and identify the relevant scope for each of the different studies. Then there's the impact assessment where we evaluate the potential environmental effects. If necessary, we look at mitigation measures to minimize any negative impacts. There's typically some sort of public consultation exercise throughout those, where we engage different stakeholders. There's a reporting process where we summarize our findings. Then there's a review and decision-making process. And then if the project gets approved, there's typically some sort of monitoring and compliance process to ensure any mitigation measures are implemented effectively. So different countries have their own EIA regulations, though many follow international guidelines from bodies like the UN and the World Bank. In the US, under the National Environmental Policy Act, federal agencies must assess environmental impacts before approving major projects. In the EU, there's an EIA directive, which requires member states to conduct EIAs for projects with significant environmental effects. And then the UK follows an EU-style EIA requirement under the town and country planning regs. Other countries across the world have similar approaches, but ultimately all have the same objectives. So now onto this particular project that I mentioned. I'm going to read verbatim off the project's website, as that provides an ideal overview of the project scope and objectives, also saves me from poorly paraphrasing. So the Morocco UK power project will be a new electricity generation facility entirely powered by a solar and wind energy combined with a battery storage facility. Located in a renewable energy rich region of Morocco, it will be connected exclusively to the UK via 4,000 kilometers of high voltage direct current subsea cables. The first of its kind project will generate 11.5 gigawatts of zero carbon electricity from the sun and wind to deliver 3.6 gigawatts of reliable energy for an average of 19 hours a day. This is enough to provide affordable, clean power to the equivalent of over 7 million British homes. And once complete, the project will be capable of supplying 8% of Great Britain's electricity needs. Alongside the consistent output from its solar panels and wind turbines, an on-site battery facility will provide sufficient storage to reliably deliver each and every day a dedicated near constant source of flexible and predictable clean energy for Britain, designed to complement the renewable energy already generated across the UK. When domestic renewable energy generation in the UK drops due to low winds and short periods of sun, the project will harvest the benefits of long hours of sun in Morocco alongside the consistency of its convection trade winds to provide a firm but flexible source of zero carbon electricity. So WSP are leading the offshore aspects of the project in collaboration with several other companies. So here's I think this is a bit of an outdated org chart now, but it's the main objective of this project is to deliver a full environmental impact assessment for each of the jurisdictions at which the cable passes through. We've currently only delivered the UK EIA, and the rest of the jurisdictions will be kicking off later this year. So as you can see, it's a healthy sized project delivery team across several marine disciplines and international jurisdictions. I particularly worked closely with our colleagues and friends at APEM, which is a small marine specialist consultancy in the UK. Oh, yeah, and there I am in the org chart. So here's a nice graphic that illustrates the full extent of the project, including the sections of subsea cable within each jurisdiction. The final design cable route is 2,363 miles. The route has been designed to, where possible, avoid environmentally sensitive areas, wrecks, unexploded ordnance, challenging geological features, etc. The design also ensures that the water depth never exceeds 700 meters, And this is to make sure the subsea cable market actually has enough cable to make the project a reality. The proposed cable installation methodology will involve laying 2 bundles of cables between 50 to 180 meters apart, where these huge mechanical trenches, as shown here, with normal sized humans as a reference, will be deployed behind a vessel and create a 1 to 1.5 meter deep trench, which the cable will be laid within. Once the cable's laid, it will then be buried by laying rocks or general seafloor type aggregates over the top. But depending on the geological features of the seafloor, there may have to be stretches where the cable is just laid on the top of the seafloor or over existing obstacles. So there's a couple of YouTube links there of trenches in action. If anyone's interested, then I'm sure the slides will be shared after this. So at the top here is, in my opinion, a fantastically executed graphic, thanks to Microsoft Word, which illustrates a cable laying vessel and the vessel controlling the trencher. Bottom left is a screenshot from an animation of some cable burying taking place. And the bottom right is a diagram of where an obstacle may need to be traversed, like an existing pipeline, where additional burial would be required. So that's a very, very high level overview of what's being proposed and some of the activities which will generate noise emissions. We'll see later on there is a larger list of noise sources we will need to consider within the assessment. So unlike other marine disciplines, where they are typically specific to one receptor group, like marine mammals or fish, etc., underwater noise is an impact pathway that affects multiple receptors. So ultimately, this means our reporting inputs into the EIA end up being a little simpler than the other disciplines, as we aren't the experts in a single receptor, we're the experts in how the sound gets to those receptors. So broken down different steps to approaching underwater noise in the context of EIA. So step 1 is to identify our noise sensitive receptors, their subsequent sensitivity to underwater noise, and where available, identify appropriate hearing threshold criteria. So for this step, it's important to note that there is a significant lack of research on auditory responses of marine species due to anthropogenic noise, i.e. human-made noise. Industry standard thresholds of various species are continually being updated. And also the regulators and clients are asking for more and more detail around the effects of noise on an increasing variety of marine species. Unfortunately, due to that lack of research, many receptors have to be scoped out of the underwater noise assessment. And I'll talk more on this shortly. So step 2 is to then identify a modeling methodology. Then we would calculate and or assign proxy source noise levels to use within our methodology, then predict the noise propagation within our study area. We'd compare our model outputs against our criteria, and then we'd provide some sort of generic conceptual mitigation recommendations if they're required. So I'm going to get a little technical here, sidestep into some basic underwater acoustic principles before we look at the hearing threshold criteria. So I'm sure you're all aware of the mighty decibel, and that it's a unit that can be used to represent the magnitude of audible sound. So on the left here is our sound pressure level formula, where we can see how our decibel is expressed as a logarithmic ratio between the given pressure and a reference pressure level, where pressure is measured in pascals. So a logarithmic scale is useful for when a physical quantity can vary over many orders of magnitude. In the case of sound, humans can perceive sound pressures from 20 micropascals to 1 million micropascals. So a linear scale would require working with crazy numbers and it would just be impractical. So logarithmic scales compress this into something just much easier to work with. One key difference between airborne sound and underwater sound is that the reference pressure is different. In air, we use 20 micropascals, and underwater, we use 1 micropascal. In practice, this typically means when you see underwater noise levels, you get comfortably up above 200 decibels. But if you had a sound pressure of 200 decibels in air, that's akin to being next to a nuclear bomb exploding. So not something we deal with often. And I've had it before when consulting with local communities on offshore wind type developments, and they've made claims that they'll be exposed to levels of 230 decibels in their backyards due to piling noise. And we've had to gently explain that that isn't quite the case. So in underwater acoustics, we've got a bunch of different metrics that describe the type of underwater sound we're dealing with. The hearing threshold criteria for marine mammals and fish are typically provided in peak sound pressure level, which is the maximum instantaneous sound pressure during a noise event, a cumulative sound exposure level, which is the cumulative sound energy over a certain time period of multiple noise events, and a root mean square pressure level, which is a time averaged sound pressure level. It's also important to note that the hearing faculties of marine mammals and fish are different to that of humans. Some of you may have seen for in-air acoustics, we often refer to decibels as dBA, where A represents a weighting that reflects the hearing faculties of humans. For marine mammals, there is an M weighting. For fish, there have been different versions of weightings which have been proposed, but they haven't stuck. So as it stands, the most recent research does not include any weightings for fish auditory sensitivity. So the first step in the assessment process is to identify the relevant receptors we need to be considering. This is something where we would liaise with our ecology colleagues, and they will provide us with a list of species within our study area. With marine mammals, the most widely used hearing threshold criteria was published in 2019 by Southall and a number of other researchers. This provides us a framework where species are split out into a bunch of different hearing groups. So here you can see we've got very high frequency cetaceans, which typically include harbour porpoise and several oceanic dolphins. Harbour porpoise are normally the marine mammals which have the highest sensitivity to noise, especially in UK waters. Then we've got our high frequency cetaceans. We've got bottlenose dolphin, common dolphin, pilot whale, beaked whale, sperm whales. Then low frequency cetaceans, and I can't remember how to pronounce that word. The Mysticetes species, maybe. And then we have our faucid carnivores in water, which are our harbour and grey seals. And then with fish, the most widely used hearing threshold criteria was published in 2014 by Popper. Similarly to the marine mammals, this provides a framework where fish with different auditory functionality are split out into different categories. And these categories are typically or are defined by how the fish's swim bladder is involved in hearing functionality. And for those who don't know, a swim bladder is an internal gas-filled organ in bony fish that functions to modulate buoyancy, and some species is part of their sound pressure detection functionality. As I mentioned earlier, where there's a lack of research and subsequently no widely used auditory threshold criteria for certain receptors, we typically scope them out of our assessment. And the authors of the corresponding aspect chapters within the reporting of the EIA tend to qualitatively assess any likely adverse effects associated with underwater noise. These chapters are typically benthic ecology, which is our seafloor dwelling species like crab and lobster and invertebrates. Other marine users, which is typically divers, and then marine archaeology, where we have protected wrecks, which might be sensitive to vibration. I've seen quantifiable criteria for some benthic species and for divers, but they usually have pretty loose derivations and don't really add much value to the assessment, unless the ecologists consider otherwise. So provided here, the marine mammal hearing threshold criteria for the project. These are specific to continuous noise, as this project involves only continuous type noise sources, such as vessel noise where engines are running consistently, some continuous drilling noise and dredging noise. We do have criteria for impulsive noise sources, such as impact piling, but those aren't applicable for this project. So the next step is to identify an appropriate and proportionate modeling methodology. So underwater noise propagation is complex, and there's several different factors which affect it. So these include the reduction of sound away from the source due to geometrical spreading, absorption of the sound by the seawater and the seabed, interaction with the sea surface, interaction and transmission through the seabed, the refraction of sounds due to the sound speed gradient, the bathymetry, which is your varying water depth between source and receiver, and the depth of your source and your receiver. There are many good resources to provide an overview of modeling methodologies appropriate for environmental impact assessments. However, no specific modeling approach is recommended above another. So for some context on the different modeling approaches, here are some graphics that nicely illustrate a simple modeling solution and a more complex modeling solution. So on the top left, we have a practical spreading loss solution, which is a simple approach that does not take into account many of the site-specific environmental inputs and is just much more generic. The graphic shows this approach is clearly very uniform and simple. The bottom left is a parabolic equation solution, which clearly takes into account more of the complexities of the marine environment. And the graphic on the right shows the level difference between the two, where we can have a variation of around 20 dB in the far field. This can obviously have quite significant effects on how we report our impacts, but also highlights the practical spreading loss solution is much more conservative in how it approximates noise propagation. So despite the limitations of the practical spreading loss approach, it's a widely accepted methodology for EIA type assessments. And due to the low risk nature of the noise sources for the project, i.e. they're not particularly loud, and to keep costs low for the client in terms of computational resources, we decided to go with the simpler practical spreading loss approach. This was subsequently consulted on and agreed with all the relevant stakeholders prior to undertaking the assessment. I appreciate I'm getting a little technically heavy here, so I won't dive into too much of the detail, but the practical spreading loss in its most simple form is represented here. I'm sure if there are any of you with a physics background, you may recognize the n log r type regression, but with a couple of extra aspects representative of underwater noise propagation. So several other technical steps we have to go through to utilize this modeling approach, which includes consideration of hearing weighting functions for different species, but we won't get too deep into technical weeds for this presentation. So the next step is identifying proxy source noise levels to input into the model. As mentioned before, data are few and far between for a lot of these specific noise sources. and deep literature reviews are required to find any existing measurement data. You'll see here, for example, where an HDD has been proposed for a source, the only data we've been able to find were measured at a nominal distance from the source. Therefore, we've opted to use better data for similar geotechnical site investigation type work, which are considered to have greater efficacy in the context of this assessment. And for those not familiar with HDD, this stands for horizontal directional drilling, and is a drilling methodology.
Tomorrow, what time can you come? After.
Yeah, okay. For those not familiar with HDD, this stands for horizontal directional drilling, and is a drilling methodology to get under unmovable obstructions. We presented the data as ranges here, but in the modeling itself, we've used the upper limit as a worst case. So this table presents the impact ranges for each of the species and each of the sources. So these impact ranges reflect the worst case distance at which the different effects are likely to take place. So one thing I realized I didn't mention beforehand is what those different effects were for the marine mammal species. So you can see we've got on the table, we've got PTS and TTS. So PTS is a permanent threshold shift, which means the hearing functionality of the different marine mammal species is kind of permanently damaged and permanently changed. So it's like a physiological injury. Whereas the TTS is temporary threshold shift, and that's akin to if you go to a loud concert, and then afterwards, when you're in a quieter environment, you like hear the ringing in your ears, and your just hearing isn't as sensitive, and it takes a while to recover. Yes, so one key limitation I haven't mentioned yet about the practical spreading loss approach is that it assumes all the receptors are stationary for the duration of the noise exposure. So in practice, and I appreciate this is a bit of a difficult one to get your head around, this means that these impact ranges are representative of the receptor being stationary at the furthest distance from the source at which the corresponding effect could take place. Obviously, in reality, the receptor will be in transit and will likely flee away from the noise. So the impact ranges we see here are very much a worst case approximation. You also see with the TTS effects, we have some pretty large distances. I think we get up to almost 17 kilometers for low frequency cetaceans. And that also highlights the practical spreading loss approach overestimating in the far field, which we mentioned earlier. So in the UK, where projects are deemed nationally significant infrastructure projects, they go through a phase of additional consultation, where prior to submitting the full EIA, a preliminary EIA report is submitted, which is a slightly less detailed version of the reporting aspects of an EIA. It's essentially a consultation tool that allows stakeholders to make comment. In the case of this project, I had the Marine Management Organisation, which is the government body that decides what happens in UK waters, come back and ask me to deviate slightly from the practical spreading loss methodology and make the fleeing responses of marine mammals an intrinsic part of the modelling. So I amended the model and factored this in. I won't go into the details of that now, but it was done successfully. And then if anyone's interested, then please do reach out and I'll happily explain how that worked. So as you can see here, this is quite a dramatic effect on our results, where we predicted that PTS effects won't take place for any species, and the worst case TTS impact range is less than 1 kilometer. And here are my references, and that's it. Thank you. So any questions?
All right. So that was
a lot of information and appreciate it. And obviously, this is the first time we heard anything about acoustic